everybody. Good morning. Myself, Dr. Shubhankar Sen from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fifth lecture of the third module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall illustrate the implementation of different kinds of boundary conditions for heat transfer problems involving a single finite element. We shall consider different combinations of essential, natural, convective and radiative boundary conditions and find out the solutions for the temperature distribution. Now, we shall illustrate the implementation of finite element method subject to different combinations of boundary conditions for an one-dimensional bar element. We shall consider a single element and we shall illustrate the implementation of essential, natural, convective as well as radiative boundary conditions. Poisson equation of heat conduction in one dimension is given by k del square T plus Q equals to 0 or k d2T dx2 plus Q equals to 0. When we perform Galerkin finite element discretization on this strong form, we generate element level matrix equation system. The GFEM discretized element level matrix equation system for this strong form is given by KETE equals to FE for a bar element with two nodes. We have 2 by 2 KE, T1E, T2E, then we have FE. Now, for the Laplacian operator and for the given source term, the element level matrix and vector, they are given as KE equals to K by delta x minus K by delta x minus K by delta x, K by delta x. This is 2 by 2 and FE equals to delta x by 2, delta x by 2, where the source term is present here. Now, for three-noded or quadratic bar element, without derivation, we write the element level matrix equation system as the element level matrix equation system is KETE equals to FE, where K to 7 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, 16 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, 7 by 3 delta x, T1e, T2e, T3e equals to q into delta x by 6, 4 delta x by 6, delta x by 6. So, for the 2-noded and 3-noded bar elements, these are the expressions for the element level matrix and vector equation systems. So, this is for the 2-noded bar element. We have local nodes 1 and 2. We have T1e and we have T2e. For the 3-noded bar element, our nodes are 1, 2, 3 at the local level. Local temperatures are T1e, T2e, T3e, and the element size is delta x. Now, using 2-noded bar elements and 3-noded bar elements, we shall illustrate the implementation of essential, natural, convective, and radiative boundary conditions, various combinations. First, we consider the essential boundary condition. Case 1, EBC at both nodes of a 2-noded bar element. Let us consider a rod of 1 meter long with specified EBCs as 100 degrees centigrade and 50 degrees centigrade at its left and right boundaries. The thermal conductivity of the rod material (1 watt per meter degree centigrade) and rate of heat generation is 1 watt per meter cube. Find the temperature distribution. So, this is the rod x-axis. This is x equals to 1 meter. This is x equals to 0. This is at 100 degrees centigrade. This is at 50 degrees centigrade. The governing equation is k d2t dx2 plus q equals to 0 and k equals to 1 watt per meter degree centigrade, q equals to 1 watt per meter cube. Consider 2-noded bar element. A single bar element. So, this is the single bar element. This is delta x equals to 1 meter. This is element E. This is E equals to 1. So, this is T1E. This is T2E. T2E is 50 degrees centigrade. T1E equals to 100 degrees centigrade. Since temperature at both the nodes is known, we have nothing to solve using two-noded bar element. So now we shall consider the next level of bar element, that is the three-noded bar element. Therefore, we consider a three-noded bar element. Now, this is the three-noded bar element where delta x equals to 1 meter. This is local node 1, local node 3, and this is local node 2. So we are having T1 1, this is element 1, equals to 100 degrees centigrade. T3 1 equals to 50 degrees centigrade. T2 1 is the unknown quantity which we have to find out. Now we know the element level matrix equation system. We generate the IEN array first. IEN array. IEN AE equals to capital A. This is E. This is A. So only one element. Local nodes 1, 2, 3. So the local nodes corresponds to the global nodes. So local node 1 is corresponds to global node 1. Local node 2 of this element corresponds to global node 2. And similarly for the local node 3, we have the global node 3. So this is our IEN array where this capital A are the 1, 2, 3 terms. Capital A is the global node number. Now we generate the ID array. For the ID array, we replot the mesh, then we see that we have only one equation at the center of the element. There, that equation number is 1. At the boundaries, the equation numbers are 0. So we have, these are the P quantities. So from here, we can construct the ID array as IDA equals to P, and this gives us A versus IDA as global node number 1, 2, 3. At global node number 1 and 3, equation number is 0 because we are given the solution already. At global node 2, we are left with only one equation. So we shall generate only one FEM discretized equation, and that is at global node 2. Okay, and if we generate the LM array, so this is LM array, we get it as LMAE equals to P. So here E, A, I, A prime or B prime or NEE. So for element 1, our local nodes are 1, 2, 3. Our degree of freedom per node is 1. So for element level equations, we can have maximum 3 equations. So those equations can be maximum of 1, 2, 3. Now for the first element, first local node, the global equation number is 0. For the first element, second node, the global equation number is 1. And for the first element, third node, our global equation number is 0. So we have our LM array ready. Since this is only single element problem, there is no assembly procedure for this case. So the element level equation, it represents the global equation. Since we have only one element, the assembly process is absent. Element level equation system also represents the global matrix equation system. Now, the element level matrix equation system is KETE equals to FE or K1 T1 equals to F1. This gives us thermal conductivity into 7 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, 16 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, 7 by 3 delta x. Our degree of freedom is T11, T21, T31. Our known right hand side vector is Q into delta x by 6, 4 delta x by 6 and delta x by 6. So we have a 3 by 3, 3 by 1, 3 by 1 matrix vector equation system. If we look into this equation system, then we find that T11 and T31, they are the known quantities. So T11 and T31 are known quantities. Therefore, equations 1 and 3 are redundant. So we solve only for equation 2, which is given as minus 8k by 3 delta x into T11 plus 16k by 3 delta x into T21 minus 8k by 3 delta x into T31 equals to 4q delta x by 6. Now we are given k equals to 1 unit, delta x equals to 1 unit, q equals to 1 unit, T11 equals to 100 degrees centigrade, and T31 equals to 50 degrees centigrade. Substituting these values, we get minus 8 by 3 into 100 plus 16 by 3 into T21 minus 8 by 3 into 50 equals to 4 by 6. So this gives minus 800 plus 16 T21 minus 400 equals to 2, or T21 equals to T1 equals to 1202 by 16. This is equals to 75.125 degrees centigrade. So, using the quadratic bar element, we can find out the temperature at one point. Now, we illustrate the case of combined boundary conditions, EBC at the left boundary and NBC at the right boundary. First, we consider the two-noded bar element. So, this is case 2, EBC at left boundary and NBC at right boundary. So here we consider at the right boundary we have 1 watt per meter square heat flux specified at the left boundary, T equals to 100 degrees centigrade. This is x equals to 0 and this is x equals to 1. So this is 1 meter. Now we use the single bar element with two nodes, local node 1, local node 2. Here these are the capital A things. So IN array E A, local nodes 1 and 2, element 1. So the global nodes are 1 and 2. Now this is the IN array. Now we generate the ID array. So here this gives us equation number 0 and equation number 1. This is NBC, this is EBC, global equation number P. So A versus IDA, it comes as global node 1, equation number 0, global node 2, equation number 1. Then we generate the LM array. Here we have EAI and NEE. E is 1. This is 1, 1 and 2. At local node 1, our equation number is 0, and at local node 2, our equation number is 1. So this is our LM array. For the single element problem, there is no assembly procedure. Now we go to the element level matrix equation system. KET equals to FE. Here we have KET equals to FE contributed by the source term plus FE contributed from NBC plus FE contributed from EBC. So this gives us the left hand side coefficient matrix K by delta x minus K by delta x minus K by delta x, K by delta x. This is the element level stiffness matrix. Here the first equation, if we see, this is T11, the second degree of freedom at the second node. This is the only unknown quantity. This is T21 equals to, from the source term, our contribution is as delta x by 2 and delta x by 2. From the natural boundary condition, our contribution is Q0 or QR, which has been specified at the right side boundary. So this is Q right equals to 1 watt per meter square. So this is 0 plus Q0. Now the essential boundary condition part, it will be shifted from the left side to the right side. So this portion is written as delta x by 2 and delta x by 2 plus q0. Now, our first equation, it is redundant because the first equation is already solved in terms of the given solution. So, we remove the first equation and we consider only the second equation. So, it is written as minus k by delta x into t11 plus k by delta x into T21. T21 is actually T1 from the LM array. T1 equals to delta x by 2 plus Q0. So we get from here K by delta x into T1 equals to delta x by 2 plus Q0 plus K by delta x into T11. So this is the source term, this is the NBC term, and this is the EBC term. So from here we get the solution. Our K is 1, delta x is 1, so T1 is the unknown, delta x is 1, so delta x by 2 is 0.5, Q0 is given as 1, Q0 or QR, the given heat flux is 1 unit, plus K by delta x, this is 1 by 1, and T11, it is 100 degrees centigrade. So from here we find that T1 equals to 101.5 degrees centigrade. 101.5 degree centigrade. So this is the temperature at the right boundary. We are finding that the temperature at the right boundary is more than the temperature at the left boundary. Now we illustrate the implementation of EBC and NBC for a quadratic bar element. Let us consider a quadratic bar element. At the left boundary we have EBC, at the right boundary we have NBC. So at the right boundary Q0R is specified as 1 watt per meter square, and here for EBC the T0 is given as 100 degrees centigrade. So this is x equals to 0, this is x equals to 1. Here we discretize the domain with 3 nodes, the local or global nodes 1, 2 and 3. This is for element 1, and the mesh size is delta x. So this is the x direction. So the temperatures are T11, T21 and T31. T11 is given as T0. This is equals to 100 degrees centigrade, and Q0R heat flux is specified as 1 watt per meter square. So this is EBC plus NBC implementation using 1D quadratic bar element. Our element level matrix equation system is KETE equals to FE, or 7K by 3 delta x minus 8K by 3 delta x, K by 3 delta x minus 8K by 3 delta x, 16K by 3 delta x minus 8K by 3 delta x, K by 3 delta x minus 8K by 3 delta x, 7K by 3 delta x. The degree of freedom vector is T1E, E is 1, T2E and T3E. for E equals to 1, and the right hand side load vector is Q delta x by 6, 4Q delta x by 6, and Q delta x by 6. Our ID array can be constructed as global equation numbers 0, 1, 2. This is capital P. So A versus IDA 1, 2, 3. These are the global nodes. This is 0, 1, 2. This is for the ID array, and the LM array is LM AE equals to P. This gives us E 1 A I N E E 1, 2, 3, 1, 1, 1 for the IDOF. Local equation numbers are 1, 2, 3. For the first local node, our equation number is 0. For the remaining nodes, our equation numbers are 1 and 2 respectively. So we generate the ID array. Now, for this case, with the essential boundary condition known, the element level matrix equation system, it reduces to K221, K231, K321, K331, T1, T2 equals to 4Q delta x by 6, Q delta x by 6. This is the load vector contribution from the source term. The temperatures at global nodes 2 and 3, these are T1 and T2. These are the unknown quantities. Then we have the contribution from the flux boundary condition, or NBC. At the second node, no contribution. The full contribution is given to the third node, that is Q0R. Then we have the last contribution from the essential boundary condition. This is minus K IBE TBE. For the second equation, local node is 2. So I equals to 2. So it is K 2. Now B is local node 1. So K21, E is 1, 1. TBE, B is 1. So T1, 1. E is 1. For the second equation, our I is 3. So minus K3, B is again 1, E is 1, and T1, 1. So this construct the equation after implementation of the boundary conditions. We can put the values. So K221, this is 16K by 3 delta x. K231 equals to minus 8K by 3 delta x. K321 is minus 8K by 3 delta x, and K331 is 7K by 3 delta x. Here the degree of freedom is T1, T2. The right hand side load vector is 4Q delta x by 6 minus K211 T11. Here it is Q delta x by 6 plus Q0R minus K311 T11. So we can substitute the values here. From here, our Q is 1, delta x is 1, K211, this is minus 8K by 3 delta x. K311 equals to K by 3 delta x. Our K is 1. T11 equals to 100 degrees centigrade. So we know all the property values, and then we can generate these two equations separately and we can solve them, it is found that the solution will be T1 equals to 100.875 degrees centigrade and T2 equals to 101.5 degrees centigrade. So case 3, NBC at both the ends. So here we have QL equals to 1 watt per meter square and QR equals to 1 watt per meter square at both the boundaries. This is x equals to 0. This is x equals to 1. In this case, when we generate the ID array, the degrees of freedom temperature is unknown at both the boundaries. So we have equation numbers at both these nodes. The ID array is generated as A versus IDA. At global node 1, equation number is 1. At global node 2, the equation number is 2. So these are the global node numbers and global equation numbers also. So this is the ID array. Now, if we generate the element level matrix equation system, we know that KET equals to FE for this case with two noded bar element, we get K by delta X minus K by delta X minus K by delta X, K by delta X, T1 1 and T2 1, this is element 1, equals to delta X by 2, delta X by 2 plus Q left and Q right. So this gives us K by delta X minus K by delta X minus K by delta X, K by delta X, T1, T2 equals to delta X by 2 plus QL and delta X by 2 plus Q right. In this case, if we see the left hand side matrix, KE is linearly dependent or KE equals to K is a singular matrix. Therefore, matrix K is not invertible or we do not have a solution for this problem. So this is an interesting case where we find that the natural boundary conditions at both the boundaries, it does not alter the element level or the global matrix equation system, particularly the coefficient matrix for the two noded bar element we are showing. So the rows of the matrix and columns of the matrix K, they are linearly dependent, and because of that this matrix K is a singular matrix and we cannot solve for this system. So if we solve this problem with quadratic bar element or with multiple elements, it is found that this feature does not change. So this is an interesting case where we find that this is the rare case where we do not have a solution other than this. Whatever the boundary condition sets we use, we have solutions. So we have already shown the implementation of essential natural boundary conditions by using two noded or linear and three noded or quadratic bar elements. Now we shall consider the case of essential and convective boundary condition using two noded bar element. So this will be case 4, EBC and CBC. convective boundary condition at the boundaries. So, if this is the single element at the left boundary, our T11 is given. At the right boundary, H and T infinity, this is given. Here, delta X equals to 1 equals to L. So this is local node 1, local node 2. They also represent the global nodes 1 and 2. So for this case, here at the right boundary, temperature is unknown. So if we generate the ID array, so we see that at the left boundary, equation number is 0. At the right boundary, the equation number is 1. So our ID array will be like A versus ID A 1 and 2. At first node, equation number is 0. At second node, the equation number is 1. Now, the element level matrix equation system, it can be constructed as Ke conduction plus Ke convection equals to Fe due to source plus Fe due to convection. This can be written as K by delta X minus K by delta X minus K by delta X, K by delta X, T11, T21 plus 0, 0, 0, H, T11, T21 equals to delta X by 2, delta X by 2 plus 0, H, T infinity. So this can be written as K by delta X minus K by delta X minus K by delta X, K by delta X plus H. This is the convective heat transfer coefficient. T11 is already given and T21 is unknown quantity, that is T1 equals to delta X by 2, delta X by 2 plus H T infinity. Now, first equation is redundant. It is not considered. So, we have the second equation. From the second equation, we get minus K by X into T11 plus K by delta X plus H into T1 equals to delta X by 2 plus H T infinity. This gives us T1 equals to delta X by 2 plus H T infinity plus K by delta X T11 divided by K by delta X plus H. So, by putting the values of K, delta X, H, T infinity and T11, we can find for the unknown degree of freedom at the right boundary. Similarly, we can use the NBC and CBC combination and we can just generate it. Case 5, NBC at left and CBC at right boundary. So this case was with two noded bar element. We can extend this problem with the three noded or quadratic bar element. So let us consider the NBC and CBC combination. For NBC, the degree of freedom is unknown. So global equation number is 1. For CBC, equation number is unknown. So here, the global equation number is 2. So these are, now, this is the mesh size, delta X. So our ID array A versus IDA, this is 1, 1, 2, 2. So at the left boundary, QL given. At the right boundary, H T infinity given. So this is NBC and right boundary is CBC. A small correction here. The temperature vector is missing. So we represent the temperature vector here. KET equals to FE system for combined NBC and CBC gives K by delta X minus K by delta X minus K by delta X, K by delta X, T11, T21 plus 0, 0, 0 H contribution from the convective boundary condition. This is the augmentation part, augmentation of the coefficient matrix. We have already told in the previous weeks that the convective and radiative boundary conditions, they augment the element level coefficient matrix equation system. So here this is T11, this is T21. We have the source term contribution delta x by 2, delta x by 2. Then we have the NBC contribution. This is QL 0, and then we have the CBC contribution 0 HT infinity. So from here we can write the matrix equation system as K by delta X minus K by delta X minus K by delta X, K by delta X plus H T1 T2 equals to delta x by 2 plus QL delta x by 2 plus HT infinity. Now we have to solve this system of algebraic equations for finding T1 and T2. Solve this system of algebraic equations to find T1 and T2. Now we consider the radiative boundary condition. So that comes as case 5. We consider combined CBC at the left boundary and RBC, the radiative boundary condition, at the right boundary. So at the left boundary we have been given H and T infinity. Here the degree of freedom is unknown. At the right boundary, where we have the radiative boundary condition, there also we have the degree of freedom unknown. So we have two equations, 1 and 2. Here the emissivity is epsilon, absorptivity is alpha, and the radiation received, that is QR double dot. So we have two unknown temperatures. These are the global equation numbers. So ID array will take the form A versus IDA 1, 2, 1 and 2. Now the element level matrix equation system, that is also the assembled equation system, because here there is no assembly. We can write it as K1 T1 equals to F1. Here we have three parts in the matrix: the contribution from the convection part, contribution from the radiation part, and contribution from the diffusion part or the thermal conductivity part. So we have K by delta X minus K by delta X minus k by delta x, k by delta x, T11, T21 plus H0, 0, 0, T11, T21 plus 0, 0, 0, epsilon sigma T1 to the power 4, T2 to the power 4 equals to delta x by 2, delta x by 2 plus H T infinity 0 plus 0 alpha q r dot. So here this is the conduction or diffusion matrix. This is the convection matrix. This is the radiation matrix. This is the source term. This is this convective boundary condition CBC, and this is the radiative boundary condition RBC. So if we combine the conduction and convection terms, then we get two contributions in the matrix, k by delta x plus h minus k by delta x minus k by delta x, k by delta x, T1, T2. So here we get T1 as unknown, T2 as unknown, plus 0, 0, 0, epsilon sigma T1 to the power 4, T2 to the power 4 equals to delta x by 2 plus h T infinity, delta x by 2 plus alpha q r dot. So this is the final matrix equation system when we have convective and radiative boundary condition at the extremities. So the radiative boundary condition introduces non-linearity into the matrix equation system. So this portion is non-linear. Now this matrix equation system can be solved by nonlinear equation solvers to find the unknown temperatures T1 and T2. Here the Gauss elimination and Gauss-Seidel type of linear equation solvers will not work. If we linearize this equation, then we can use the Gauss-Seidel method. So Newton-Raphson type of methods can be used for solving this system of nonlinear algebraic equations. Now we show the last case where we use the radiative boundary condition at both the boundaries of a two-noded bar element. Obviously, all these cases can be extended to the three-noded quadratic bar element. So the last case is case 6, RBC at both the boundaries. So we have the left boundary properties epsilon 1, alpha 1, QRL double dot, epsilon 2, alpha 2, QR right double dot. Sigma is the Stefan Boltzmann constant. So in this case, T is unknown at both the nodes. T is unknown like the previous cases we are showing. So this is the FEM mesh size. This is delta x. This is 1. Now T1 and T2 are the unknown quantities. The element level matrix equation system is k by delta x minus k by delta x minus k by delta x k by delta x T1 T2. This is contribution from the conduction term or the diffusion term. Now this matrix is augmented by the radiative boundary condition at both the left and right boundaries. For the left boundary, the contribution is epsilon 1 sigma 0 0 0 T1 to the power 4 T2 to the power 4. This is RBC contribution at left boundary. For the right boundary, we have a similar contribution. Here, the terms corresponding to T2, that will only be non-zero, so 0, and here it will be epsilon 2 sigma T1 4 T2 to the power 4. This is RBC contribution at right boundary. Now we have the source term delta x by 2 plus we have the contribution from the RBC at the left boundary, that will be alpha 1 QRL double dot 0, and for the right boundary it will be 0 alpha 2 QR right double dot. So we can combine the right hand side vectors into a single vector, and then the matrix equation system, which is both local and global, can be rearranged as k by delta x minus k by delta x minus k by delta x k by delta x T1 T2 plus epsilon 1 sigma 0 0 0 T1 to the power 4 T2 to the power 4 plus 0 0 0 epsilon 2 sigma T1 to the power 4 T2 to the power 4 equals to delta x by 2 plus alpha 1 QRL double dot delta x by 2 plus alpha 2 QRR double dot. So for all the cases except for the set of natural boundary condition at both the boundaries, we get that the left hand side coefficient matrix, that is linearly independent, and because of that in every case we get the unique solution. When the natural boundary condition prevails at both the boundaries, the matrix equation system becomes linearly dependent and we do not have unique solution for that case. So we can put different input values for the epsilon, alpha, h, t infinity, k, delta x, these quantities that have appeared in our considered examples, and we can solve for the temperatures at the unknown nodal points. We have also shown some examples for the quadratic bar elements, and those can be extended for the any kind of boundary condition set that we have defined. Now we illustrate the case of RBC at both the boundaries considering a single element. So we have a single finite element of 1 unit length. In this case, RBC is specified at both the boundaries. So we are given with epsilon alpha at both the ends, epsilon 1 alpha 1 and epsilon 2 alpha 2. we have to find T1 and T2 at the left and right boundaries. So in this case, here we are showing the global matrix equation system which is obtained from the element level matrix itself without assembly, since this is a single element problem. So RBC at both ends. This gives nonlinear algebraic equations. So we have two unknowns, T1 and T2, so we shall get two nonlinear algebraic equations. In the first case, the matrix which we are getting, that is coming from the conduction or diffusion contribution for two noded bar element. This is the radiation contribution. This contribution is from the left boundary and this contribution is from the right boundary. This portion is the source term and this is the contribution from RBC. The top one is at the left boundary and the bottom one is at the right boundary. Then we get the, here we get the compact form of the matrix equation system. This is the compact form. Now substituting these values here, we have put epsilon 1, epsilon 2, alpha 1, alpha 2. These values along with the value of the mesh size and the Stefan-Boltzmann constant. In this case, temperature must be in Kelvin. This is a very important condition for the radiation problems. Then we got two nonlinear algebraic equations. This is the system of two nonlinear algebraic equations. After solving these equations by Newton-Raphson type of nonlinear iterative equation solvers, we get these two values, temperature 248.429 Kelvin and another one is 248.909 Kelvin. These are the very nearby values. Now I just mentioned here that for NBC, CBC and RBC in one dimension, the boundary nodes act as single noded point element. For this element, we have only one shape function psi 1e such that psi 1e equals to 1 by virtue of the condition summation of psi I equals to 1, where I varying from 1 to any n. So for a point element, we have only one node. Because of that, we have only one shape function. Now for the Lagrangian shape functions, summation of all the shape functions should be 1. So by that argument, the shape function for single noded point element, it will be unit valued. Now we can show this for the Neumann boundary condition. Let us consider this is a boundary element, local node 1 and local node 2, and here this is the NBC term given by Q0R. So heat flux is specified. Now the boundary condition term is gamma E psi I E K del T del N d gamma E. Now we get a single noded point element with Q0 are specified. For this particular case, at the right boundary, we have nx equals to 1. This term can be written as boundary integral over gamma e psi I e nx del t del x plus ny del t del y d gamma e multiplied with k. This is in 2 dimension. In 2D, in 1D, this becomes gamma e psi I e k del t del x, del will be d, k dt dx into d gamma e. Now, it is found that whether we consider the left boundary or the right boundary, depending on this normal to the surface nx minus 1 or nx equals to plus 1, the boundary flux term, it becomes k dt dx. So, this quantity k dt dx as a constant term, it comes out. So, this is k dt dx integration over gamma e psi I e d gamma e. Now this term becomes 1 for a point element so from here we get k dt dx into 1 equals to Q0R at the right boundary. Okay. Similarly, for the convective boundary condition, we can show the contribution. So we should remember that for the implementation of boundary conditions at the boundary flux term, the element order, it reduces. It means that for implementation of NBC, CBC or RBC, the order of the boundary element reduces. The meaning is that this is a boundary element E, boundary element E with 2 nodes 1 and 2. It acts as a single noded point element. Single noded point element. Similarly, if there is a boundary like this on which we have a quadrilateral element with local nodes 1, 2, 3 and 4. Here Q0 is specified. This reduces to nodes 2 and 3. Q0 element E. So quadrilateral element reduces to a 2-noded bar element 2, 3 as shown above. So we conclude today's class here. In today's class, we have presented the treatment of EBC, NBC, CBC and RBC under various combinations for 2 or 3 noded bar elements. It is interesting to note that the NBC combination leads to a singular matrix equation. For today's class, I suggest the textbook of Professor J.N. Reddy. The textbook by Professor Hughes should also be followed in connection with the different pre-processing arrays. Thank you very much for attending my lecture.